Hello everyone, my name is Avant Mehta and welcome to my homework for ordinary least squares fitting. I'm going to conduct this homework in two steps. The first part is I'm going to talk about the introduction to OLS and then I'm going to show you my app. And in the second part of the video, I'm going to talk a little bit about matrices and how we do some basic addition, multiplication, transposing, etc. So this is actually labeled as a homework even though it's lab sized. So let's get into it. First, we'll talk about the basics of OLS. So what is ordinary least squares fitting? Well, the whole objective is that we have to fit a polynomial as best as we can of a given order onto a given data set that we're going to have. Our order refers to the highest term of x that's going to be in the fitting polynomial. So for example, in the quadratic case, as you can see over here in equation 1, the highest term of x is x squared, hence power of 2. And that's what makes it a quadratic. And we have over here y equals theta 2x squared plus theta 1x plus theta naught plus e, where y represents the real y data and x of course represents the actual x data. The theta variables represent the parameters of the optimal fit of the polynomial. So these are like the coefficients that multiply with the respective powers of x. And then we have e, which is the error term or the residual, and that tells us how far our polynomial of best fit was to the particular data point. And that's going to be a key concept because the point of this is to find the optimal polynomial such that the errors are minimized. So that's important. We can write the compact form over here as y bar equals a times theta bar plus e bar, where y matrix is actually a single column and it has the same number of rows as the number of data points. We have the A matrix, which is basically just the powers of x, and this changes by size depending on the order. And every row is the same in this matrix, but the columns change by the power of x. So we have on the right side x to the 0, which is 1, then we have x1 and then x1 squared. So I mean to say actually it's x to the 0, x to the 1 and x squared. And then we have the theta matrix, and these represent the parameters which ultimately will tell us what the fit is by its coefficients. That has as many rows as the number of data points. Sorry, my bad. As many rows as the number of the order. And then we have our error matrix, and that has the same as the number of points. So here we have the equation for the sum of the squared errors, and that's what we're going to try to minimize. The sum of the squared errors is the summation from 1 till the number of data points of the error residual squared. And this can also be written as the E matrix transposed multiplied by E. And next up we have to find the optimal parameter vector, that's the theta, and that means theta equals A transposed multiplied by A all to the power of minus 1 multiplied by A transposed multiplied by Y. And that's the equation we're using to find out the polynomial of best fit by getting all the theta values from this equation. Next, we're going to work our way to getting the coefficient of determination, which is not to be confused with the regression coefficient, as is more commonly referred to in statistics. That tells us how good the fit is. If it's 0, that means it's really, really bad, and if it's 1, it's perfect, and if it's something like 0.99 or very close to 1, that tells us that we're doing a really good fit. So we have the sum of the squares of residuals, and that's SSR, and that's actually very similar to what I just covered. Then we have SST, which is the total sum of the squares, and that SST is the summation from 1 till n of yi minus y bar whole squared, where y is the mean of the y values given in the original data set, and yi represents each individual y value as predicted by the polynomial itself. And hence we take the difference in each case for all the n data points and then square them individually and then add them all together. And finally, we can get our r squared value, the coefficient of determination, by doing r squared equals 1 minus SSR divided by SST. So that was the introduction to ordinary least squares. Now I'm going to show you the app that I've built. And as you can see from the graph over here, we're going to load some data of pressure drop across an orifice, where on the x-axis we have the flow rate in cubic meters per second, and on the y-axis we're going to have the pressure drop in megapascals. And this is the example we're using, but actually this can be any kind of data at all. So as you can see in my app, I've disabled the order and fit button and spinner, and that will be activated when the data set is loaded. So let's go ahead and do that. I click on load over here, and then I choose the data over here that I want to load up, and I click open. And then I can press my fit button to load my data. And I've put in my scatter plot each individual point from the data set. And my red line over here is going to be my line of best fit. In this case, it's a constant because I've set the order to be 0, so it's not a function of x. And I can change my spinner value over here for my order, and I can make it as high as 6. I've set a limit on the spinner. And I've also made it, as you can see, auto update my line of best fit equation as well as the line on the graph as I change the order, so it live updates over there. And if I change my order to 2, I have an r squared value of 0.9596, which is fairly high. If you look at the data points, you can clearly see it's not looking like a straight line, so we do need a higher order than 1 at least to get close. So if I do 2, again it's 0.9596. If I change the order to 3, I've already gone above 0.98, and if I make it 4, we've already gone above 0.99. So it doesn't really get so much better beyond order 4. We've already gone above 0.99. And again, my best fit line over here, the equation over here is displayed in its entirety in case you want to plug in any different point and use that. For the next part of this video, I'm going to have a look at the questions that were asked, and they're all related to matrices. So let's get into it. First, what is the dimension of a product of an n by m matrix times an m by 1 vector? So the way we go about this is first we check the compatibility, that is, can we multiply them? And the way we check that is, we look at the number of columns of the first matrix, which is m, and we look at the number of rows of the second matrix, which is also m, and because they match, they're equal, that means we can multiply them. And the resulting dimension of this output matrix is going to be the number of rows of the first matrix by the number of columns of the second matrix. Hence we have n by 1 matrix or vector because it's actually a 1 dimension, and on its columns is going to be the output dimension. Our second question is, what is the dimension of a product of a 1 by m vector times an m by 1 vector? And what is the name of a matrix with this dimension? So just like we did before, first we check compatibility. Number of columns here is m, and number of rows on this one is also m, so they match. The dimensions will be the outside values, that is the rows here and the columns there, so it's 1 by 1. And the name of a matrix of a 1 by 1 matrix is a scalar. But here's the thing, it doesn't really function like a 1 by 1 matrix per se. What it does function like is that you can use that scalar to multiply it by every value in another matrix you're going to multiply that scalar with. Third question is, what is the dimension of a product of an m by 1 vector times a 1 by m vector? And for the third time, we have to check compatibility. It's 1 by 1 for the columns here and the rows here, so it's compatible. The outside values tell us the actual dimension of the product. That's m by m. Hence we have an m by m matrix as the output. And because we know that it has as many rows as it has columns, it's going to be a square matrix. Question 4, based on the given scenario, what order of polynomial would you think would be appropriate to fit here? And should it be a polynomial at all? So that's for this data over here. And I think that the order should be 3. But first I want to note that in the notation that they use in this homework, in the question itself, when they refer to order 3, they're using a quadratic graph, but I refer to quadratic as order 2. So the reason why it shows that order 3 is fine is simply because I think having order 4 is unnecessary, because I think that order 3 is enough to get the job done, because its R squared value was 0.9928, which is actually very close to 1. So there's no need to have it as high as 4, because 3 does the job sufficiently. And if you look at the graph, you know that it's not linear. It does look like a curve, so we do want some polynomial of at least quadratic nature. So I think that order 2 will not be a high enough order to get the job done, to get a close enough line of best fit. So I think order 3 is fine. And should it be a polynomial at all? I think I answered that. It's because it doesn't look like a straight line, so we should use a polynomial of at least quadratic nature. Question 5. Sometimes instead of a vector product, we simply want to multiply all the entries of the vector with each other, resulting in a vector of the same dimension as the original vectors. How does one do this in MATLAB? So there's a command in MATLAB. I wouldn't say command, but it's an operation that you can use as an expression, which is the dot asterisk, or the dot multiplied by. And if you do, for example, have matrices A and B, and you want to find C being not the dot product, but multiplying the entries of the two vectors with each other individually, you do A dot star B. And that is actually used in question 16, as we're about to see in a little bit. And that's how it's done. So next up, we have all of these questions. We were given A, B, and C as these particular matrices. The values were given to us. This part of the video is going to be a bit drab, because I'm not going to explain every individual answer, but I'll just show the output. So A plus B is 11, 18, 5, 6, 11, 9, 13, 2, 10. A times C is 33, then 14, then 13. A transposed is 4, 3, 8, 9, 5, 1, 2, 7, 6. A inverse is all of this. Question 14, that is C transpose multiplied by C, that's just 14. Question 15 was C times C transpose, that's 4, 6, minus 2, 6, 9, minus 3, minus 2, minus 3, 1. Question 16 is C dot star C, and as we just looked at a minute ago, this is the same syntax that's used, not to indicate the dot product, and not to be confused with either, but multiplying the rows individually. And that becomes 4, 9, 1. As you can see, they're actually squares of the C matrix. 2 squared, 3 squared, and minus 1 squared is 1. Number 17 is A transpose times A whole inverted multiplied by A transposed multiplied by C, and that is this 0.4528, and then 0.3389, and then 0.3806. And that is the end of this video and the homework, and thank you so much for watching as always.